Network architecture relies on a strict rule. Single points of failure are unacceptable. Redundant backup links are mandatory to ensure reliability. But unmanaged redundancy is inherently dangerous. This diagram shows a minimalist three-switch topology. If a backup link activates without any control mechanism, it connects the three nodes into a closed physical circuit, a literal loop. The problem begins the moment a single data packet enters this triangle. Because it is a broadcast frame, the first switch duplicates it and sends it out of all other active ports, sending copies traveling in both directions around the closed circuit. Every switch follows the exact same rule, forwarding broadcasts out of all ports. This means these frames never expire. They hit the next switch, duplicate again, and continue looping. They multiply exponentially, instantly saturating the connection lines. What begins as just one single frame becomes an expanding vortex of traffic, overloading and destabilizing the physical infrastructure. This creates a broadcast storm. The endlessly circulating radiation consumes all available bandwidth, leaving no room for legitimate user traffic, which is simply dropped. Simultaneously, switch MAC address tables become corrupted. The same source addresses appear on different ports at the same time, causing the switch to constantly overwrite its internal routing maps. Within seconds, the entire network grinds to a complete halt. Performance degradation is absolute. Redundancy without a strict control mechanism is structurally fatal. To survive, the network requires a system that physically prevents links from activating the moment they are plugged in. Spanning Tree Protocol, or STP, is the architectural solution to this exact problem. STP prevents broadcast storms by intentionally slowing down the activation of backup ports. It refuses to let them forward traffic immediately. Instead of turning on right away, a port must clear a strict sequential series of operational phases known as port states. Plug a cable into a standard unmanaged switch, and the port lights up instantly. Plug a cable into an STP managed port, and it halts, remaining inactive to data while it evaluates the environment. These states decouple physical connection from logical network integration. The port must mathematically prove it is safe before admitting a single frame of user traffic. The first and default STP phase for redundant links is the blocking state. This diagram shows the internal logic. It receives a unified traffic stream, splitting it internally. User data routes towards one gate, control traffic routes to the CPU. In the blocking state, the port drops all user data to prevent loops. Traffic disintegrates, hitting a closed red gate. The port also refuses to learn any MAC addresses from these discarded frames. However, the port is still listening for Bridge Protocol Data Units, or BPDUs. These vital control traffic messages map the topology. The blocked port actively listens and processes these BPDUs. They bypass the data blockade entirely, passing through the open control gate directly to the CPU. The blocking state is an act of active surveillance. The port is dead to user data, but fully alive to the network's topology. If a network failure occurs, like a severed primary cable, that blocked port is forced to begin its activation sequence. It enters the second phase, the listening state. Notice how the logic gates behave. The data plane remains locked down. User traffic is dropped, and MAC learning remains disabled. The state's sole function is verification. The switch rapidly exchanges BPDUs with neighbors to verify if advancing this port will inadvertently create a loop. The listening state prioritizes control plane agreement over data transmission. It is an absolute safety check before the port takes another step toward activation. Only after the port passes the topology safety check does it transition into the third phase, the learning state. Even in this phase, user data payloads cannot pass. The red gate stays closed. However, a new scanner mechanism activates. The port extracts source MAC addresses from blocked data packets before discarding the payload, using this data to populate its internal routing table. Skipping this step would be disastrous. If the port started forwarding traffic with an empty MAC table, the switch wouldn't know where any devices were located, forcing it to blindly flood all packets out of every port. The learning state prevents this flooding. It synchronizes the switch's internal map, ensuring that the moment the link goes live, routing is efficient and targeted. This brings us to the final transition, the forwarding state. The port is now marked as fully integrated and operational. The data plane opens. The gate turns green. and user traffic finally crosses the switch fabric to its destination. MAC address learning continues dynamically as new traffic arrives on the active link. BPDU processing also continues uninterrupted, allowing the switch to constantly monitor for any future network changes. Reaching the forwarding state means the switch has mathematically proven the link is safe. It has fully prepared its internal routing logic and safely restored data flow without risking the wider network. This complete, sequential journey from a topological change to a stable forwarding network is called STP convergence. This timeline charts the exact process. The port moves from blocking into listening, then learning, and finally forwarding. This meticulous transition requires time. In classic STP, clearing these states takes up to 50 seconds. For devices relying on that backup link, 50 seconds represents a complete network outage while the switch evaluates the topology. This delay is not a glitch. It is the exact amount of time the protocol dictates is necessary to guarantee absolute loop prevention. Classic STP strictly trades operational speed for architectural stability. In early, less critical network environments, a 50-second outage was an acceptable insurance policy against a total broadcast storm. But in modern, high-speed data centers, a 50-second convergence delay causes unacceptable, catastrophic application timeouts. The strict, slow mechanics of the classic STP state machine became the primary catalyst for engineering a faster successor, Rapid Spanning Tree Protocol.